happy to have Shahrzad Haddadan to join this ALGO seminar. She's currently a postdoctoral researcher at Brown University, working under supervision of Professor Eli Upfal. Shahrzad's expertise is to employ combinatorial structures and statistical tools to model massive data problems. Her area of research includes study of social issues in online networks, analysis of algorithms using MCMC, and study of primary problems in graph mining in different computational models. She received her PhD from Dartmouth College, where she was working under supervision of Professor Peter Winkler. Today, she's going to talk about reducing polarization and increasing diverse navigability in graphs by inserting edges and swapping edge weights. Please welcome our speaker.
Thanks, everyone, for having me here. I'm Shahrzad Haddadan. I'm a postdoc at Brown, and this is a joint work with Cristina, Menghini, Matteo, Riondato, and Eli Upfal. In particular, Cristina, who was a main collaborator. So the talk today is about reducing polarization in online networks, and I will divide this talk. It's actually a combination of two talks. One is about reducing polarization by inserting edges, and the other one is about increasing navigability. I will explain what I mean by that by swapping edge weights. So I will first tell you what is the motivation of this problem and how we model it differently from prior work. And then I will talk about these two sub-problems. So filter bubbles have been a topic of discussion in the past decade. And initially, social scientists and internet activists like Eli Upfal started talking about filter bubbles and how they limit our exposure to the internet. And then after this work of social scientists, there was some work in the computer science domain in quantifying through mathematical measures controversy on social media, or analyzing the impact of filter bubbles, or coming with algorithmic solutions to mitigate these effects. Now, if you look at the work of social scientists, the effect of filter bubbles are discussed from two angles. One is when they discuss or talk about echo chambers, and the other one is through epistemic bubbles. Now, echo chambers are when it's a situation when beliefs are amplified or reinforced by communications inside a closed system, and they're insulated from rebuttal. What does it mean? It means that when you hear a view that is aligned with your prior belief, you don't challenge that view, you accept it easier, rather than if you see something that is not aligned with your prior belief. So it's a property that individuals have. But epistemic bubbles describe a situation when the structure of a social system is in such a way that the views that are not aligned with your proper belief are left out. So if you want to compare them, in epistemic bubbles, other voices that are not aligned with me are not heard. And in echo chambers, other voices are heard, but they are actively undermined. So you can say the echo chamber is a property, is a behavior of individuals or society, but epistemic bubbles are structured in the network or in our society, etc., etc. Now, if you look at this prior work on modeling filter bubbles or controversy on internet, you will see that the modeling is done in a way that vertices describe the users in a network, and edges describe relationship between these users. Like if in Facebook, if they have friendship, or in Twitter, if some users retweet each other a lot, the modeling is based on that. In other words, it's a mathematical model for echo chambers, and there's not much work done to mathematically model epistemic bubbles. On the other hand, there is some observational and experimental studies which actually show the existence of epistemic bubbles in some networks, for example, Wikipedia or YouTube. this work on Wikipedia is the work of my co-author and colleague, Cristina Menghini, who observed that, for example, in Wikipedia, if you look at some polarized topics like abortion, you will see that the network nudges users to explore pages about just one side of a topic. Or you can see the same thing in YouTube, that if you look at the graph that is built by the recommendations of the videos, users may take pathways in YouTube that radicalize them in their prior beliefs. So the first part of my talk is I'm going to talk about information networks. And this is a work that was published in Wisdom and was a runner-up for Best Paper Award. And then I will tell you how we generalize these ideas and to use them for recommender systems. Okay, so bubble, in this talk, I will first define bubble radius. This is a mathematical term to model episomic filter bubbles. Then I will tell you how we use bubble radius to find the structural bias in a network. And then I will talk about some algorithms that aim to mitigate this bias in a network. So assuming we have a graph G with a vertex set V and a set E, this graph is directed and the edges are weighted. Here V presents the pages in a network. So for example, if you have Wikipedia, you can think that each vertex in this network is one page in Wikipedia. And then you put an edge from one vertex to another one if there is a hyperlink from this edge to the other one. Now, we assume that these vertices are red or blue, and these colors present the leaning of a page on a polarized topic. So for example, if you consider the topic of abortion, you can say the red vertices are pro-life pages and the blue vertices are pro-choice pages. Now here you can see that our modeling is different from prior work, and it's just looking at the structure of the network that is built by Wikipedia. Now I have to also talk about how we model the behavior of the users. So these users would navigate these networks. And to model the behavior of users, we introduced bounded random walks. So what are bounded random walks? We pick an upper bound T, which is an upper bound on the exploration session of our users. And we say a bounded random walk is basically a normal random walk which takes 2 steps and stops. So in other words, let's say a user enters the network from here with a probability proportional to these weights. He or she takes this edge or that edge and continue doing this, taking 2 steps in the network, and then he or she stops. Now I define the bubble radius for each page in this network as follows. Let's say I have a vertex V here. I let C bar of V the set of all the pages with the opposite color. So here it would be all the set of all red vertices. Now I say the bubble radius of V is the expected number of steps that we need to take to reach the opposite color. Now remember that this is a bounded random walk, so this value can be at most be T. Now, if you are familiar with the terminology in random walks, this is the hitting time to the red vertices using bounded random walks, something like that. So now, note that now that we have made this random walks bounded, we have a very nice, it behaves very nicely because it makes computation much easier. Now, the variance and range of our random variable is bounded, so easily with Monte Carlo estimation, we can find the bubble radius for all of these vertices. Note that if we don't have this, we have to calculate the Laplacian of matrix, like if we were looking at normal hitting time, we had to calculate the Laplacian of matrix and etc., which is computationally more expensive than Monte Carlo estimations, especially when T is small. So now we want to use this measure to quantify polarization of a node. we want to say some of these vertices are good, some of these vertices are bad. Basically, some of these vertices are more surrounded by pages that are like themselves, and some of them are not. So here we capture this definition by introducing parochial vertices. Parochial vertices are those which are basically captured by the vertices or pages of their own color. So we say if the bubble radius is greater than t over 2, this node is parochial. And then we denote the set of all parochial nodes of the same color, C, with curly P of C. Now, based on this definition, we define the structural bias of the graph with respect to color C as the sum over all parochial vertices of their bubble radius. So now I want to talk about some of the algorithmic contribution. So the question we ask is how to reduce the structural bias. So we fix the color C, let's say blue or red, and then we ask what can we do, let's say, what can we do to reduce this structural bias if our strategy is basically inserting links. So we first formulate this problem as follows. So let's say I want to get rid of all of the parochial vertices, or in other words, I want to take down the structural bias, take it down to 0. Now the question I ask is, what is the minimum number of links that I have to add to this network to achieve this goal? We show that this problem is hard to approximate within large factor, and I will show that in a second. But then, since this problem is not really tractable, then we change the problem formulation and we ask, if I'm limited to just add a fixed number of edges to the network, how can I, where should I add these vertices so that to minimize the structural bias in the new network? For this problem, we suggest an algorithm and we show that it approximates the optimal solution under some assumptions. So the hardness problem is shown by reduction to the set cover problem. It's a not very difficult reduction. So remember what is our problem? The problem is we want to pick a minimum. So let's say we are concentrating on color blue. So I want to pick minimum number of blue vertices and connect these vertices to red, to some vertices in there with color red, so that no parochial blue vertex is left. And remember that the set cover problem is we have a set of subs. We have a universe U, and we have a set of subsets of this universe. And we want to pick minimum number of sets that cover all of this universe. And we can show the set cover problem by a bipartite graph, which and these edges show the membership between these elements and these sets. So let's say I have an instance of the set cover problem. I change it to a bipartite graph, and then to reduce it to problem 1, what I do is I color all of these vertices of the bipartite graph to blue. Then to each of them, I attach a path of length, let's say t over 2 minus 1, a little bit smaller than t over 2. And then I attach all of them to a vertex of color red. Now, the parochial vertices in this network are U1, U2, U3 to UN. The rest of them are good. So the problem that I have is to add some edges to this network so that the bubble radius of these parochial vertices, which are U1 to UN, falls smaller than T over 2. Now you can see easily that this is a reduction to the set cover problem, because we can show that it's not in the optimal solution. You would never connect any UI to red. So everything all the edges would either be from these parts to the red vertex, and any edge that is like in this path, we assign it to the set that is connected to it, and then it gives us a solution to the set cover problem. Now, since we know that the set cover problem is hard to approximate within log factor, and this, if we assume that t is constant, this is an L reduction, then we conclude that the problem one is hard to approximate. So now we formulate the problem in a different way. We say that the number of edges that we want to add to the graph is fixed, and we want to minimize the structural bias. Now, remember that the structural bias is, this is the formula of the structural bias, which is sum over all parochial vertices, the bubble radius. So here, so far I was just saying, I was all the time saying, we want to add some number of edges to the graph, but we can also say we want to choose some vertices in the graph and connect them to the opposite color. So now we want to minimize in this new graph the structural bias. But here we are abusing notation a little bit, because this is not the structural bias of the new graph, because we are still taking the sum over previous parochial vertices. So this is not exactly the structural bias of the new graph. Now, how do we solve this problem? To minimize the structural bias, I maximize a gain function. So the gain function is basically the difference between bubble radii of all the vertices which are parochial in the original graph, and we take the average over all of them. Now, we show that this delta is monotonic and submodular. Now, monotonicity is easy, but here I want to discuss submodularity a little bit. So let's look at this formula. Here we are summing all over parochial vertices. So let's say W is a parochial vertices. So what does submodularity say? So if I look at here, I want to say the difference between B of original and B new, if I add two vertices, two edges at a time, is smaller than the gain I get by adding each of these vertices at a time. So in other words, if I want to say if I change G to GUV, the gain I obtain is smaller than the gain I would have got if I had added U to G or if I had added V to G. Now, if I rearrange these terms, what I will get is that the gain that I will get in a graph by just adding U to E to the original graph. So just consider this situation. Actually, I have this picture which looks nicer. So I have two graphs. They are identical. In one of them, V is connected to the opposite color. In one of them, it's not. So this graph has one extra edge. So now, to both of these graphs, I connect U to the opposite color. The gain that I get here is more than the gain I get here, which intuitively you can kind of get an understanding why it works, because when things are too bad, like here, adding one edge gives you more gain than here. So how does this proof work? The proof works by, so let's just consider the gain we get here. The gain here, we get it if we condition on the fact that a bounded, so let's say a bounded random walk starts from this parochial vertex W. We will achieve a gain if we pass this edge. So I can break this gain conditioning on the event that I pass this edge. The same for here. Now the difference between this graph and this graph is that I may pass V with I may pass the gray edge that takes me to red earlier than I pass the red edge. So the gain would be condition that I pass this edge earlier than the gray edge. So if you write the arithmetics, you will see that it will work out. And because this condition is more narrow than this condition, then the submodularity works. Now, since this gain function is submodular, we know that if we, at each iteration, we pick V among all parochial vertices greedily and connect it to the opposite color, then this will give us an approximation algorithm. Now, the question we ask is, what is the greedy choice? Now, let's say these are all of my parochial vertices, and this is one candidate to be connected to the opposite color. If I connect this vertex to the opposite color, then I will also change the bubble radius of some other vertices. These vertices are those who had a large bubble radius, like greater than t/2, and the bubble radius was not too large to not be affected by this connection. So we obtain a set here, and let's say now I'm considering connecting this node to the other color, and this affects another set of vertices. So the vertices which are more central with respect to this bounded random walk will give us more gain if they are connected to the opposite color. So we define a new centrality measure, which is basically the average of closeness with respect to the bounded random walk. So if you look at this expected value is basically the number of steps and you need to reach this vertex itself, but we are actually taking t minus this expected value, which is a measure of closeness. Okay, so now if now we can show that if I pick a vertex among all of the parochial vertices with maximum random walk closeness centrality, then this gives me an approximation to the greedy choice. Now, why still approximation? We are still missing this factor 4 times gamma of g plus 1. Now, what is this gamma g? This gamma g is the number of times that a bounded random walk returns to the vertex when we started the random walk from. So where does this come from? So let's say I have connected this vertex to the opposite color. So the first time that I'm starting my random walk, I have a chance of traversing this edge and I will get some gain. But this may not happen. I may just take some steps and then get back to it after several steps. Then I will have another chance to traverse this vertex and get some gain. So basically you can see that the more I have in this bounded length random walk, the more I have a chance to traverse this edge, the more is the gain that I would obtain. So that is how this term comes from. Now, if you put all of this together, so basically I showed that my objective function is submodular, and I showed how to approximate the greedy choice. So my algorithm is basically looking among all parochial. First, it finds all parochial nodes of color C, then it computes the random walk centrality of all of these nodes, and then it looks at the vertex which has the maximum random walk closeness centrality. We also have to multiply it by the weight of this edge that we are adding, which we just make some heuristic assumptions about it in our experiments, and then we connect this to the opposite color. Now, using all of the lemmas that I showed, we can show that this approximates the optimal solution. This 1 plus 1 over epsilon comes from the submodularity, and this other term comes from the fact that our greedy choice is just approximation. So we have run this algorithm, our algorithm on some data. We basically compare it to some existing methods for link insertion, because these do not incorporate any fairness measure. So, and they, as you see, they don't really change the structural bias, but this red diagram plot is showing our algorithm. This purple one, we don't use random, we don't use the centrality measure to connect the vertices to the other part. We just choose them randomly. And you can see that as we increase the number of links to add to the network gets saturated and they eventually meet. But before that, our algorithm has a better performance. So now I want to change the discussion by motivating why we should care about link swaps. So the motivation here comes from recommender systems. So bubble radius, I started motivating bubble radius by saying that we care about epistemic filter bubbles. But in fact, bubble radius is kind of showing polarity of navigation in a network. And we argue that polarity of navigation is harmful also in recommender systems. It's not only a problem in knowledge networks. Now, recommender systems are usually, they have some diversity measures already incorporated in them. For example, it is known that, for example, if your recommender system, like your Yelp, knows very well that you prefer, say, Italian food to Indian food, but they still, when they give you a suggestion of restaurants, they show everything, both of these options in your searches. But it is still shown by people in social sciences, etc., that in some recommender systems, like YouTube, when they recommend you the next video to watch or other things, there are some users who actually navigate the network for a number of steps, and their views got more radicalized by doing so. The other point about comparing recommender systems to information networks is that there are different motivations and different ways of making these graphs that make them very different. So we cannot treat them the same. Now, in the next couple of slides, I want to convince you that instead of link insertion, we should consider link swaps in a graph like YouTube. And instead of just caring about parochial vertices, we should care about all the vertices. So in information networks, we modeled this problem by saying there are some parochial pages, their bubble radius is greater than t over 2, and we define the structural bias as the sum over all of these. But in recommender systems, basically, firstly, with our observations, we found out that if we pick the same modeling, like if we pick the same definitions, we don't find many parochial vertices in the, for example, the dataset that we were looking at was Netflix. We don't find many parochial vertices. So we got rid of this definition, and instead we looked at diverse navigability. So here, instead of parochial vertices, we are just looking at all of the vertices of that color. The other thing is, in information networks, you can, inserting a new edge has very low cost. So for example, I can say this is a Wikipedia page for abortion, let's say. And I just decide that if I make a link here and connect this to Cairo program of action, this will make the bubble radius of this page smaller. But this has not a big cost for me. I can easily put a link here. But recommender systems are more profit-based than a network like Wikipedia. And we also cannot add these links very easily. Like I cannot easily suggest, say, phones to people who are looking for shoes. So we need a strategy that is less costly than link insertion, and we suggest swapping the edge weights. Now, how can we do that? Let's say in a Spotify, for example, I have just listened to this actually IMDb, I think. I have just watched this movie, and there are these suggestions for me. I just try to swap the order of these suggestions, and this means that people would have a higher probability of clicking on the higher order suggestion, and we are basically changing the probability of clicking on these vertices. Now, again, we ask a similar question. Let's say I have a color C, and I want to swap some links. I want to basically choose some vertices which have color C, and swap some links with that are adjacent to these vertices to increase diverse navigability. So here we can also show a hardness result, but I didn't write it here. But instead, we also have two different algorithms. One of them is we fix the number of edges that we want to add. We want to swap in the. We fix the number of vertices which we want to modify, and here we suggest shuffling. And the other problem, instead of saying the number of vertices that want to be modified, we say that each swap of pairs of edges has some cost for my network, and I want to do this swap within a budget. So here I suggest another algorithm. So again, here we have run our experiments, and we get a better comparison with respect to other methods. Now, in conclusion, I like to summarize our work from three different aspects and talk a little bit about how I think these results can be improved. So the motivation of this paper is that we think polarization in some networks like Twitter or Facebook have been studied a lot, but with some other networks like Wikipedia, the studies are rare. So we try to study the polarization of such networks, and we model it by the structural bias. The way we model the user behavior is by introducing the bounded random walks, and after introducing the bounded random walks, we had to also introduce other measures in the graph, which is basically bounded random walk closeness centrality. Now, I think what would be an interesting add-on to this model is like, what if we model this problem using geometrically stopping random walks? Like, if I say that at each step the walk stops with ratio of 1/t, then the expected value of the walk is still t. How much of these methods would generalize and how much of them won't? I think many of the results would work. The other thing is our algorithm is greedy, and we use submodularity of the objective function. But when you think about this problem, you would think that this is a lot like a flow problem. We are basically saying that we are basically thinking about the flow of information in the network. So maybe it could also be formulated as a min cut or max flow problem. These are the areas that I don't understand much. But from another perspective, conductance of a graph is also, I think it would be interesting to think of it from that aspect, and if it's in a relationship with mixing time. So maybe by using these other techniques, the approximation ratio that we have would improve to some extent. And thanks.
Thank you, Shahrzad, for the talk. Are there any questions from the audience? I actually have one question. Can you talk a little bit more about the open question on the flow-related problem? Like, if exactly
Yeah,
what the problem is?
yeah. I haven't. As you said, I'm not really expert in max flooming cut, but what I think is that this parochial. We are identifying these vertices like the parochial vertices in a way that it's hard to reach the other color. If I start white here, it's hard to reach the other color. In other words, you can think of there are some bottlenecks in this network that don't allow these vertices to reach the other color. So intuitively, you would think that maybe instead of identifying parochial vertices, it's better to identify these bottlenecks between the red and blue vertices. We are doing it the opposite way, kind of.
Interesting. Yeah, makes sense. Any other questions?
I have a question or two. Are there any studies about how user behavior changes after these extra links are added, or the order is swapped? I mean, do we know how effective they are in reducing not just the static polarization, but user behavior in the future?
Yeah, that's a good question, but unfortunately, we don't have the resources to measure anything like that. So I guess your point is, if I do connect, for example, let's say Cairo program of action to his page, what is the likelihood that the users would actually take this edge? We haven't really studied this problem at a practical case, but Cristina has worked closely with Wikipedia for some of her projects, and the graphs that we got from Wikipedia are actually based on the probability that actually users, it's a weighted graph, and it's the probability that users actually take these edges. But for modification, we have not. I'm not sure if she's here and she has a better answer to this question. For modifications, we have not really done that study because we don't have the resources. But that's a question. I don't know.
Yeah, I was thinking for recommender systems, you'd be able, if you had a dynamic, system that people were using, like Movie Lens, you could actually do social experiments where some users get extra links and others don't, and then you watch how their preferences change over time, something like that.
Yeah, I think it will be very interesting if we have the resources to do such studies.
Okay, thanks.
I think Cristina is on the call. Did you want to add something, Cristina, to the Shahrzad's answer?
Hi, sure. So yeah, the on Wikipedia, it's kind of really difficult to try to measure whether the addition of new edges as having an impact. At least it's very difficult to do in a short period of time because it would require recording it for longer periods. As Shahrzad was saying, Wikipedia collects and makes public the number of clicks for each link, aggregated by the month, but it would be, I mean, I tried to talk with the guys of Wikimedia Foundation, asking them whether it was even possible to maybe set up an experiment to control a bit how users behave and move, not only especially with respect to polarizing topics, but unfortunately this is really sensitive matter because it would require user to ask for being tracked, and it's kind of difficult to know to do it on specific topics and what you are interested to recording the phenomenon. And more in general, if instead one can think about synthetic experiments where the navigation of users is simulated instead of realistically observed, this is kind of difficult in general for Wikipedia because still there is no a model that generalizes user behavior. And I would say that in the case of polarization, maybe it would be even harder because it would really be dependent on even on the polarization of the user itself, other than the network. Yeah.
Makes sense. Thanks for the explanation. So if there are no other questions, maybe we can unmute and thank Shahrzad for the talk.
Thank you.
Yeah, thanks.
Thank you.
Thank you.